Hey guys, welcome back. This is the third and final lesson of our three-part page ranking series. In the first lesson, we looked at what is page ranking and we looked at an algorithm to calculate page ranking using backlinks. In lesson 2, we looked at the Wikipedia page terms. We wrote a custom input format and custom pigload function. And that was the hard part. Yes, trust me, that was the hard part. In this lesson, we are going to write a pig script to calculate the page rank using what we learned from lesson 1 and 2. And this is the easy part, and I'll make it super easy to understand. We are going to walk through the script one line at a time and understand it thoroughly. Now you know your dataset, and you know the problem you're trying to solve. We already have a pigload function named pig_rank_load to extract the page title and the URL references from page for each page in your dataset. And now we have to implement the page ranking algorithm that we learned from lesson 1 in our pig script. Whenever I face a problem like this, I always try to visualize the problem using a sample dataset that I can work with on a piece of paper. And every instruction that I write, I project and note down the output as well for the small dataset. This helps me visualize the problem and progress on a solution. Look at this slide. Take this sample dataset from our lesson 1. Each box is a page, and when you use the page rank load function which we created in the last lesson, you can load this dataset like how it is shown on the screen. For instance, Apache is a page and it has URL references to Hadoop and XML. Similarly, Hadoop is a page and it has URL references to Apache, Cloudera, and XML. Spring Page does not have any reference to a page, so it is empty. Now with the formula to calculate the page rank, we can calculate the page rank of Apache. If we calculate the page rank for one page, we can apply the same logic for the other pages as well. Can you think of how you can write a pig script to rank these pages? I have a suggestion. Pause this video right now and think of how you can arrive at a solution. And write a pig script using this sample dataset on the screen. Try it. It's definitely worth the effort. Okay, did you pause and try to write the script? If you tried, great. If you're not able to finish the complete script, that is okay. I'm here to help you understand step by step. Let's look at how to load the dataset first. The very first thing you have to do is register the jar which has the pig rank load function. I've already exported the pig load function as a jar. It is very simple actually. Just go to Eclipse and right click on the project which has the load function and the XML input format that we saw on the last lesson. Just right click on the project, hit export, make sure you select the jar file, hit on next. Give a location where you would like to save this jar file, give a name to the jar file and click finish. That is it. The jar is now created. Once the jar is exported, copy the jar to the cluster. Once the jar is exported, copy the jar to the cluster. I've already copied the jar to the cluster. So simply say register, give the location of the jar right here. Now you can use the page rank load function in your script. Now take a look at this load instruction. In the place of pig storage function in our load instruction, you use the page rank load function. Now this load instruction should return a tuple with two columns, page title and a bag of URL references or page name that the page is pointing to for each page in the dataset. You give the location of the dataset and you define columns, that is it. If we loaded the sample dataset on the screen, it would display the output as shown. Make sense? The second column is a bag, that is why it is enclosed in curly brackets. The third instruction is just to remove the bad records. Remove any records with null pages. So we have a cleaner dataset to work with. So if you look at the output here, it says page Apache has two URL references, one to page Hadoop and the other URL reference to page XML. Similarly, page Hadoop has three URL references, one for Apache, one for Cloudera, and one for XML. So in the next instruction, we are calculating the points that each page can give to another page. For example, Apache has two links to XML and Hadoop. So Apache has to split the point between XML and Hadoop, and hence it can only give away half a point to each page that it has links to. Similarly, Hadoop has links to Apache, Cloudera, and XML, and hence it can give only 1/3 of a point, that is 0.33 point to each page. Let's skip the Spring page from our example for simplicity since it has no pages. Okay, let's move on to the next instruction. If you look at the records relation, the second column here is nested, meaning you have tuples inside a bag. This would make it difficult for operations like joining. So we can use the flatten operator to remove the nesting. If you look closely, the flatten operation will result in more of a cross product between the page and each of its links. For example, you can see Apache Hadoop like this, Apache XML, and Hadoop joined to Hadoop Apache, Hadoop Cloudera, Hadoop XML, like this right here. Now that we have removed the nesting, let's move on to the next instruction. Here we have two instructions. In the first instruction, we are joining number of links point per page using the page column with page link mapping relation using the link column. This will result in a data set with only pages. Meaning, if a page points to a link that is not a page in our data set, this join will remove the record, cleaning our data set. In the next instruction, we'll project two columns that we need, page and link. In our sample data set, all the links that we have are pages in the data set, so our data set is already clean. Most of the students will come this far, but thinking through the next instruction will be challenging to some. If you're projecting our sample data set as we do on screen, it will be much more easier to see the solution. Take the only good pages relation. It has a page and its link. Now ask yourself, what is needed to calculate the page rank of Apache? From the illustration, you know that Apache has links from Hadoop, Cloudera, and XML. So if you know the points that Hadoop, Cloudera, and XML can give to each page that it points to, you can calculate the page rank of Apache, correct? So from this relation, how do you get the list of links that point to a page? That is, how do we know Apache gets links from Hadoop, Cloudera, and XML? Any ideas? If you see only good pages relation as page to link mapping, you will be stuck with this problem forever. Think in reverse. In terms of link to page, Hadoop page has a URL reference to Apache, which means Apache page gets a backlink from Hadoop. Similarly, XML page has a URL reference to Apache, which means Apache page has a backlink from XML. Same for Cloudera, same for other pages as well. So if you join the page from only good pages with the number of links points per page relation, you will get the end relation like this. And then all you have to do is group the output by link. Now you can group the pages that references Apache. That is Hadoop, XML, and Cloudera. Pretty cool, right? Let's look at the grouping. It will make complete sense. The grouping is very simple. You group by the link and not by the page, and that is the key point here. And when you group by the link, you're grouping all the backlinks for this page specified in the link together. So for example, if you take Apache gets backlinks from Hadoop, XML, and Cloudera. Hence, they are grouped together. Now you know that Apache gets backlinks from Hadoop, XML, and Cloudera. All you have to do is sum the points from each page together, and you will get the ranking, which is 1.33, and that is the page rank of Apache. Finally, you can order the result by the page rank and store the result. And that is it. We are done. Here is the complete script. It is nothing but the whole list of instructions that we just saw on a file. Now let's run this script. I'm storing the page ranking results under output/PageRankPig. So let me first clear the output directory. Now that the output directory is deleted from HDFS, we are clear to run our pig script. So in our cluster, the pig script is under this location, HRW Workshop, pig, Wikipedia, and the name of the pig script. So all you have to do is say pig and the pig script name. You can also pass the input and the output location as parameters to the pig script. But in this case, I have just hard-coded the location in the script. So let's execute this script. As always, pig is going to take the script, analyze the script, and translate the script into a bunch of MapReduce jobs, and it will execute the MapReduce jobs in the cluster. Since we have a lot of operation in the script, this will translate into a series of MapReduce jobs, which will be executed back to back. As always, you can also monitor the execution of the pig script in the application URL right here. Okay, the execution is now complete. As you can see, our script got translated into a total of 6 MapReduce jobs. 1, 2, 3, 4, 5, 6. You can also verify it on the URL right here. As you can see, it executed 6 applications and it all succeeded. So let's review the output. The pig script read about 148 records. So in our case, each record is a page. So we analyzed about 148 pages from our XML Wikipedia dataset. And finally, we have ranked about 94 pages in our dataset. Some pages could have been removed because it is a bad page, or it probably did not receive a link from any other pages. So let's look at the output and let's see which page was ranked first. So output page rank pig is where we stored our output. So I'm going to do Hadoop fs cat on this file. Since it's just 94 records, let's just see the output. And there you go. Here's the output. And just for easy readability, I've copied the output locally right here. And as you can see, Apache Software Foundation is ranked way up high. An Apache license comes up next because no wonder all the other pages have links to Apache license. And also you can see Apache Hadoop and Big Data are ranked next to next in 3rd and 4th places. And Apache HTTP server is at the 5th place. You can also scroll down. Let's look at the page which got the least rank. The page that got the last rank is Alpine Data Labs. And that is it. That concludes our page ranking series. I'm sure you learned a lot from this project. But if you feel overwhelmed and if you have trouble understanding a concept, just ask the question in the course and we'll be happy to answer that. With that, let's wrap this lesson. See you in the next lesson.